Welcome. In this session, we'll explore convex sets. Our definition of a convex set will have a certain parallel with our definition of a convex function because there's a close relationship between the two of them. However, we need to understand that they're definitely not the same. So, a convex set which we can write as a double-barreled V. The way that we would draw that is something like this. And what we mean is that if we pick any point u and any point lowercase v, that the line that connects them, a straight line that connects them, is also in the set. And an example, so that would be convex, and then a non-convex example would be, for example, something that's shaped sort of like a kidney bean, where it's possible to pick a u here and a v here, and the linear interpolant between the two of those falls outside the set. So we can be a little more formal now. So suppose we have a convex set, and it is a not necessarily strict subset of the space of all vectors that have n entries. And what we mean is that for any vector u that is in this set, and any vector v that is in the set, and any value of theta that's between 0 and 1 inclusive, what we mean is, what does it mean to interpolate? Well, what we do is we take the vector u and we take the vector v. And then we take the same idea that we used for convexity of functions and we apply it to convexity of sets. And the linear interpolant of these is if we take 1 minus theta times u plus theta times v, that accomplishes this dotted line proceeding between u and v. And if this vector that is the linear interpolant of u and v, if that is also in the set, then v is a convex set. So some properties that are intuitively clear and are theorems in mathematics, so we can look them up. Properties include, but of course are not limited to, the intersection of convex sets is convex. And this is an idea that we'll use often later in the course. One that we'll use occasionally is that an affine transformation, so we already looked at an affine map in a previous session, an affine transformation of a convex set is itself convex. And what that, so this intersection of convex sets, well, we're familiar with that from elementary school when we drew Venn diagrams. That is, we would normally show something such as that, and if we have two convex sets, then this intersection set is convex. The affine transformation is somewhat less clear, because what it means is that if we expand or shrink a set linearly in each of the directions of the vector of the underlying vector space, and then we can also shift it up and down, that is convex. So we'll use one particular idea attached to this when we get to level sets. Some other properties that are worth noting is, let's recall what happens with any real numbers. So let's recall that for any real number a and any real number b, and any L that is not negative, so we say it's in the R plus. If A is less than or equal to B, then we know that L times A is less than or equal to L times B. And that says that that this inequality is preserved by multiplication by 0 or a positive number. And similarly, we recall that for any A, B, C, and D that are all real numbers, that if A is less than or equal to B and C is less than or equal to D, then we know that A plus C, that is, if we add the less than sides, that is less than or equal to the sum of the greater than sides. So the implications for convexity are that if F is convex, then if we multiply F by any by any non-negative value L, that is also convex. And if F1 and F2 are convex, then F1 plus F2. Actually, let's make that Fi and make that Fj, because I don't want to possibly confuse it with the F1 and F2 that we had in a previous session. So if Fi and Fj are convex, then Fi plus Fj as a function that maps a vector to a real number, that is also convex. So let's take some of this and let's visualize it now. Let's start by looking at the intersection. When we were in elementary school and we drew Venn diagrams, we had closed sets. And convexity doesn't require anything regarding closure, openness, finite, or infinite. So, for example, one affine set is a half plane. So we can imagine this is the W1 axis, this is the W2 axis, and we can say that the set is everything that is on this side of a line. And what that means is that this is a convex set, because if I take any point U and any point V, its connecting line segment lies within that. Similarly, I could take a different line, and I could say, let's define a half plane as being on one side of that different line. And the intersection of those two half planes, it has to be a convex set. And in this case, it has this shape to it. These little bars are simply part of the graphing function. They don't indicate that the set stops there, although if they did stop there, that also would be a convex set. So these are just illustrations, not proofs, that the intersection of sets is convex. Let's take a different example. Suppose we take an ellipse. So we have a half plane, and now if we take an ellipse is also convex. If I take any 2 points that are inside, including on the boundary of that ellipse, and I draw a connecting line segment, that connecting line segment lies entirely within the set. And when I take the intersection, what I'm doing is effectively I'm truncating that ellipse. And so a linearly or affinely truncated ellipse is also a convex set. Now, what about the sum of affine functions? We won't go through the full suite and this would be certainly good homework for you to do. But let's take those previous first and second functions that were affine maps, and they're each convex. So here we have the two of them, which we've already seen, and then when we add them up, we get a different, in this case also, affine map. So in this case, the sum of two affine maps is an affine map.